Thank you. It's a pleasure to be at this new campus. I had nothing to do with the creation of ICTS, but I've been a frequent guest. I was at the same 2009 meeting as Leon in Mahabaleshwar. Before that, I was at the 2007 meeting at Goa back in the nomadic days when the ICTS schools would move around. And then a couple of more recent things, but I've greatly enjoyed all of those, and it's great to see this wonderful campus. I'm sure there was a lot of hard work by a lot of hard people, by a lot of, well, that too, but by a lot of tough people, let's put it that way, and very talented people to make it happen. Actually, one way or another, I've been a guest of things related to TIFR for 22 years, so I'm very grateful for the generous hospitality of the Indian physics community. So this talk is about topology, and the first part, I'm actually going to explain in the simplest terms I can what is a topological phase and why are we excited about them. And then the second part gets a little bit more technical. It has a couple of equations, but I hope reasonably accessible, a little bit of calculus, that's all, which is about how do these new kinds of materials give us new electromagnetic responses. And one reason I wanted to talk about that is it's a good example of the unity of theoretical physics, which is sort of a theme of this workshop. And this involved a lot of people, mostly at Berkeley, that I'll try to mention as I go along. So some general themes to keep in mind. When we think about electrons in a crystal, normally we don't have to think about things like quantum chromodynamics and so on. We just think about electromagnetism, which is a relatively simple U1 gauge field in theory language. But it turns out that the way electronic wave functions are formed in a crystal creates a kind of gauge field, a so-called Berry connection, and those can be rather complicated. But the good news is that every quote-unquote gauge invariant object, and I'll try to say what that means in a moment, but that's one concept that is so important in theoretical physics, I hope you've heard about it before. Basically, every possibly sensible object you can make out of these special gauge fields in a crystal has a physical meaning. It controls something we can observe, like the existence of a new phase. Even if it doesn't lead to the existence of a new phase, it maybe leads to a new phenomenon, and that's been a clue in helping us understand these. And this has been a big program in condensed matter for about 30 years. It was a large part of David Thales' Nobel Prize a year ago. And then the new stuff at the end will be, we've recently found materials that realize, for example, gapless, massless Weyl fermions and Dirac fermions. Weyl fermions, we used to hope they were in the standard model. They seem not to be, but they do appear in solids, so all the things you might have found interesting about Weyl fermions like chiral anomaly and so on, you can hopefully do condensed matter experiments on. But it turns out to be a little subtle, and I'll explain that. So in addition to the unity of theoretical physics, topological phases are interesting because they have a kind of universality. A slightly more technical introduction. So these Berry phase gauge fields I'm going to define in a second are just one way to understand topological phases. The reason why they're useful compared to others maybe is they're very directly connected to how things respond to electromagnetism and very directly connected to all the hard work that particle physics has done for us over the last 30 or 40 years. So topological semimetals, it turns out to be a hard question to find what is some really unique signature in bulk of these new materials. In fact, one thing I have to say you could almost view as a no-go theorem, that what people had thought would be the interesting linear response isn't actually there most of the time, and when it is there, it's connected to something else that's quite an old property. It's not unique to these new materials. So our claim is that you have to go to nonlinear responses, which are not as well studied, if you want to understand something interesting in Weyl semimetals. And we have a particular nonlinear response that we think is the first example of a quantized nonlinear response from topology. And there are various experiments, and I'll flash up one or two. There is not yet exactly the experiment we want, but there were one or two simple experiments. There's one you can even do at home that I'll tell you about later on. So what really launched topological phases was a lucky observation in the lab, which is that if you take a material where the electrons basically move in 2 dimensions, and you do a very old standard condensed matter measurement, which is to put on a magnetic field, push electrons one way, and measure the voltage that builds up perpendicular to that, you see a strange effect. So at weak magnetic fields, you see what you expect, which is a straight line. Let me focus on the red curve, which is the transverse resistivity. But as you go to larger field, you see these flat regions emerge. And these flat regions are not just flat on the scale of pixels, they're flat to about 1 part in a billion. And if you figure out what does that correspond to in conductance terms, on these plateaus, the conductance is E squared over h, E the electron charge, h Planck's constant, times an integer, to incredible accuracy. And the reason why this is exciting or universal, it doesn't care what material I'm talking about, and it is just an integer. In fact, later on we find fractional examples and so on, which are in some ways more interesting and so on. But I just want to focus for now on the simplest class of topological phases. And topology came into trying to understand why does some big chunk of material with defects and thermal fluctuations give this incredibly precise answer. In a sense, it's quantum mechanics gives a sort of perfection out of imperfection, which is quite a remarkable thing. So, as an argument that you should pay attention to the next few slides if you care about solids, I'm going to give the simplest example of a topological phase, which is that quantum Hall effect and how that's related to a kind of curvature, a geometric property of electron wave functions. But those same ideas with various improvements continue to explain all kinds of other things. So topological insulators are a little bit more than 10 years old, and that's just a more complicated mathematical version of the same concept. And then there are plenty of things other than topological phases that sort of come out of the same approach, and I'll come back to those later in the talk. So I'm not going to try to cover nearly everything on this slide, just basically the top and the bottom. So the way we make topology in this area of physics is to take something that has a local geometric meaning and integrate it over a closed surface. So let me make a mathematical analogy of this kind of topology. So if I take two-dimensional surfaces, at every point on one of those surfaces, there are two radii of curvature in perpendicular directions, and one notion of curvature I can define is the inverse of the product of those radii, and I want to define a positive or negative sign as follows. If I take the sphere, both curvatures are away from me or both are toward me, but either way they have the same sense, and that's positive Gaussian curvature, while this hyperboloid is negative Gaussian curvature, and the cylinder is actually not curved from Gauss's point of view. So if I take closed surfaces, that's when the magic happens. If I integrate the curvature over the sphere, let's see what we get. Well, this is 1 over r squared. The surface area of the sphere is 4 pi r squared. So I get 4 pi. The magic is however I distort the sphere, as long as I don't cut it, I still get 4 pi. So it's not only independent of the radius of the sphere, it's independent of all the details of the geometry, as long as it's smoothly connected to the sphere. So that's a kind of robustness or universality that we want to find physics versions of. To show you that things can be different, if I took the torus has positive curvature on the outside and negative curvature on the inside, and those cancel out. So the total curvature of the torus is 0. So in physics language, we could say that the total curvature over a 2D surface that's closed is some quantized thing. And we'd like to make an analogy of that now for electrons and solids. So quantum mechanics tells us that an electron, if I forget about spin, is described by some complex valued function of space and time, but let's think about energy eigenstates. In a crystal, the crystal means periodic potential. Things take a simple form. There's a plane wave times something that is periodic with the same periodicity as the unit cell of the crystal. And a consequence of that is that the set of independent values of momentum k lives on a d-dimensional torus, the so-called Brillouin zone. So that Brillouin zone, a d-dimensional torus of allowed values of momentum, is going to be the surface that we use to make a topological invariant. And we need to make a curvature, and that curvature is going to come from what's sort of the hero of the talk, the Berry phase, which also goes back to the early 80s. There were examples of Berry phases well before then. Probably the earliest and most famous is by Pancharatnam. Berry sort of explained that these were all examples of the same concept. So if I take a quantum system that is in a non-degenerate state and I slowly change the Hamiltonian, then the system remains in that state. But there's another part of the story. There's something more, which is that a phase can build up. In particular, suppose my Hamiltonian is a function of some parameters, like knobs in the laboratory, and I take those parameters around a closed path. Then there's a phase that builds up, which I can write as the integral of a vector potential, or Berry connection, that lives in momentum space. So this A, this is the same letter that we use for the vector potential in ordinary electromagnetism, and that's not coincidental. This turns out to be exactly the same kind of gauge field, and I make it by taking derivatives with respect to parameter of the wave function at each value in parameter space. So this is something made out of the wave functions and how they smoothly vary. And for us, the parameter is going to turn out to be momentum in the Brillouin zone. So the way this is like a gauge field, and a gauge field is something that transforms in a certain way, and there's a whole lesson of how to make physical objects out of those and how to couple them to quantum mechanics and so on. Anyway, if I have this definition, you might worry at first, because one thing we know is that the wave function is only defined up to a phase freedom, multiplying by some phase factor here, and that phase factor is not uniquely determined. I might choose psi k, and you might choose some different phase convention. And if we do that, then this thing changes. It changes by a gradient of the phase, which means that A at one point in momentum space can't actually be physical. It's not a gauge invariant quantity. But I know from undergraduate electromagnetism how to make possibly physical things out of A. And the simplest one is just to take the curl, where again, this is the curl in momentum space. If I've got more than one degenerate state, then immediately I get a non-abelian connection instead of this abelian U1 connection. This is a note for maybe the physicists, where these are band indices. So you might ask, well, is this just mathematical playing around, or do those non-abelian connections mean anything? And I'll tell you in a moment about the first physics example we know where non-abelian Berry connections actually matter. So now's when it gets connected to topology, because this F, this Berry curvature, we call it, is a local geometric quantity. If I take a two-dimensional material and integrate that over the Brillouin zone, which is just what this integral means, this is thing in the parentheses is just F, then the magic happens. I always get an integer. It's like a winding number. It's a topological invariant, and that integer is physical, and this is what Thouless and collaborators pointed out as their picture of the quantum Hall effect, that this Chern number, or TKNN integer, there's some topological integer assigned with every set of wave functions, an energy band in a crystal, and it tells me if I put electrons in those bands, how much do they contribute to the quantum Hall effect. And so this gives a topological picture of why that quantization is so precise. So now we have many, many other examples of this concept, where something about the quantum mechanics of electron wave functions, and in particular, how they vary smoothly and give us gauge fields, tells us something physical. And now I'm going to jump to the last few years and tell you about some consequences of that. And one is going to be a link between the original work on topological insulators, which started in 2D with Kane and Mallee, and I'm going to focus on the 3D case because there the connection is simpler. How that's connected actually to earlier work in high energy physics on so-called Axion electrodynamics, basically how the axion particle would couple to matter. So the original picture of what is a topological insulator from the condensed matter community was that it's some three-dimensional insulator whose surfaces are always metallic. And in particular, their surfaces, at least in the simplest case, have a single Dirac fermion. Dirac fermion means an effectively massless fermion. So this is saying these are three-dimensional insulators whose surface is always an unusual metal. And in fact, those were found very soon after the theoretical prediction. And I won't tell you about experiments and so on, but let me tell you how, in a sense, at least if you're concerned about the universal long-distance physics, something about topological insulators was known in the 80s by a very different set of people. So people in the 1980s say we're interested in how a certain kind of particle would couple to electromagnetism. And the answer is that it would create a term like theta E dot B with some prefactor, which is actually E squared over H again. So E dot B is special because it's a total derivative. That's a hint that this might have something to do with boundaries or topology. And it was pointed out, and the most concise paper I know on this is by Wilczek in '87, that if you've got a material, so he actually thought maybe this could be realized in materials, because we know that in various materials you change the rules of electromagnetism a little bit. Anyway, Wilczek's point was that if you have time reversal symmetric materials, which is most materials, then you will generate this term, but there are only two possible values because theta is an angle, theta equal to 0 or theta equal to pi. And we now realize that theta equal to 0 are ordinary insulators and theta equal to pi are topological insulators, although you're sort of free to switch which is which if you like. And the way that connection works, to say that a material has E dot B in bulk is exactly the same thing as saying it has quantum Hall effect on the boundaries. To say that theta is equal to pi means that the boundaries must be weird. Instead of having the integer quantum Hall effect that I told you about at the beginning of the talk and said was incredibly robust, you have half-integer Hall effect. So it all hangs together only if one Dirac fermion, which is what we previously knew is the special surface state of these things, gives me a half-integer quantum Hall effect. And we actually know that both theoretically and experimentally. Here's an example of an experiment. So graphene, which will appear later in my simple experiment, it won the 2010 Nobel Prize. Some of the best evidence that graphene has Dirac fermions is that the quantum Hall plateaus basically correspond to half integers, although I have to divide by 4 because of some extra degeneracy. So it all hangs together, and just as an example of how things are connected, this is the thing with the star is the most complicated by far mathematical equation I have in the talk. Basically, if I take the non-abelian Berry connection and I integrate the so-called Chern-Simons form, so something that mathematicians and particle theorists had thought about a long time ago, this kind of integral gives me whether theta is 0 or pi. And if you're wondering how does an integral give only two possible answers, well, under time reversal symmetry, that fixes it, and gauge transformations turn out to shift theta just by a multiple of 2 pi. So in a sense, 0 and pi are the two allowed interesting values. And this actually turns out to be useful for magnetoelectricity in all materials. So without even knowing it, for 50 years, people have been measuring the non-abelian gauge fields in crystals. So now I want to come quickly to new developments, which are metals. And for a long time, we thought that metals could not be interesting topologically. We knew that this Berry phase and concepts like it were changing the theory of metals. In fact, the biggest mistake in the famous 1970s textbook on solids is that it leaves out this Berry phase term in the equations of motion for a wave packet in a metal. But the previous applications of that were not super surprising. We now realize that in some new materials that I'll tell you about, there are more surprising results. This is what I mean by not surprising. The original use of that new term in metals from the Berry phase was that if you have a metal that's magnetic, like iron or something, then there is a contribution to the Hall effect that is just the same integral I had before, except it's not over the whole Brillouin zone, it's only over the occupied part. So if that were the whole story, it's nice and it took a lot of hard work to figure that out, but it wouldn't be very topological. So there are two other effects. One is the so-called circular photogalvanic effect, which means you put right circular light on a material and current flows one way, you put left circular and it flows the other way. Keep that in your mind. That's a photocurrent, which means it's a nonlinear optical effect. It's a current going like the square of electric field. Linear optics, well, there's an old effect which turns out to be related to the chiral magnetic effect in the new Weyl semimetals I'll tell you about. So the old effect is if you take materials that are handed, like quartz or chiral, and you pass light through them, the polarization of the light gets rotated. This even happens in sugar water if you use the right sugar. But that old problem, understanding how that happens, is actually the resolution to the so-called chiral magnetic effect, which was the linear response that was thought possibly to be interesting in Weyl semimetals. It turns out that that effect is either 0, which is not that interesting. It's a topological 0, so more interesting than other zeros, but still 0. Or it's just this old effect in disguise. So what are these topological semimetals? And this is actually connected to Shankar's talk. So right after Dirac wrote down the Dirac equation in 3D, two other people figured out two different ways to take half of that equation. So Dirac's equation is a 4x4 matrix equation for an electron, say. If you make the electron or make the fermion equal to its antiparticle, that's Majorana, which you heard about. If instead you say that the particle is massless and the left-handed parts and right-handed parts decouple, that's what Weyl did. And we hoped for a while that neutrinos might be Weyl fermions, but it turns out they're not. Experiment is important in science, as you heard this morning. And experimentally, neutrinos oscillate. They have a mass, which means they can't be Weyl fermions. But we do have solids now, and this was just discovered experimentally around 2014. we have solids where at low energy, the only excitations are 3D Weyl fermions. It's kind of a generalization of graphene to 3D. In fact, we also have the Dirac case. So these Weyl fermions, people had thought about them since 1930s or so in solids, but there's a topological significance of them, which has mostly been thought of in terms of surface states. This is work by Ashwin Vishwanath and collaborators. Let me focus on, and maybe the topological significance was a little earlier. Let me focus a bit on the bulk and just how can you tell that there's this unusual massless fermion? So the first hope was there's an interesting failure of current conservation if you have a single Weyl fermion, the so-called chiral anomaly, a nice accomplishment from, again, particle physics, which is that if you have this same combination of parallel electric and magnetic fields, you spontaneously create charge, which is normally a problem. We like charge conservation, so that's why it's an anomaly. It was thought that maybe you could get rid of having to have both these fields and find the right crystal where effectively the crystal itself would produce the electric field and you would get a response that was a current generated purely by magnetic field. That turns out not to happen in the static limit. It does happen at finite frequency, but at finite frequency, so first, in the static limit, it's not that hard to convince yourself that this should be zero. There's kind of folklore that it should be zero, and a detailed calculation says if you take a material and you put it in a magnetic field, then macroscopically there's no transport current. So let me not go into the zero. The non-zero part is if you oscillate the magnetic field, then you get something. But an oscillating magnetic field, according to Maxwell's equations, produces an electric field. It's actually just an electromagnetic wave. So what you think you're computing, which is some exotic magnetic response, is actually just a response to an electromagnetic wave. It turns out to be interesting and dominated by something geometric, the orbital moment of the Bloch electron. But that's kind of a no-go theorem in a way from the point of view of new topological effects. This says that at linear response, the only new thing in Weyls is not specific to Weyls. It's there in doped quartz and other things as well. So I want to focus on what is, to me, more surprising, which is nonlinear effects. But this is saying even if I took a simple band structure like a Weyl, that linear effect is something that's material dependent. It has these energy properties of the material in it, basically not very universal, not very topological. So can we ever see something that is quantized and material independent in metals? And now I come to the simple experiment. So first, okay, this is a complicated and new experiment saying that there is something interesting nonlinear in Weyls, but first, here's an argument that things can be pretty well quantized in metals, and it's an experiment you can do at home. In fact, I think it's the simplest way to measure the fine structure constant, but you can only do it in the last decade or so because we didn't have graphene before then. So graphene is a single sheet of carbon atoms, and they can make them large enough now that you can pick one up and you can hold it up to the light. And if you do that, you'll see that you can mostly see through it, but a little bit of light gets blocked. And the amount that gets blocked is actually pi times the fine structure constant, which works out to 2.3%. So mostly transparent. But the point is it's not something that involves, I'm sorry, that's pi times e squared over hc, if you can't quite make it out. So the point is this is, again, not sensitive to the details of graphene. It's not some velocity from graphene. It's the vacuum speed of light. It's not perfect quantization. It's not like 1 part in a billion. It's more like 1 part in 100. But it's pretty remarkable. It just happens that the linear spectrum of graphene is the key. This only works over some frequency range, but it happens to work in the one that's useful for our eye. It's not very topological, but we want to find a similar optical effect that is quantized for different reasons. It's actually got a different quantum. So again, this is e squared over h with an extra factor of c. We'd like to find something different. So the circular photogalvanic effect has a long history in solids, but it's mostly been studied at low frequency. The magic I'm going to tell you about happens when I go to higher frequencies, but the idea of the effect at low frequency is very simple. Circular polarization means the electron distribution rotates, say, like that. The normal velocity cancels out in that circular motion, but the anomalous velocity, the Barry phase part, does not, at least if the material is inversion breaking. And I can do the opposite, and then the current flows the other way. That's the effect. So not super exciting, but that is measured and so on. But now let's go to non-zero frequency. And one thing about this effect is that it is measured, but it's sadly very small. If you take a Weyl material, then you can be in a frequency range where one Weyl point gets crossed by the optical transition. So the frequency of the light is this yellow distance, and that hops you across the Weyl node here, while this other Weyl node is at a different energy, so it doesn't. So basically, this node would be described by our old semi-classical theory and give a small effect. What does this node give? The answer is that, first of all, this effect gives a result which is very large. It's about 100 times larger, maybe 1,000. It's universal, and it has a nice simple expression. Basically, the current you inject in this effect for a Weyl point is some numbers times e cubed over h squared. So if this can be observed, it would be the first quantized nonlinear optical effect of this type. Here, c is a topological number, and I is the intensity of the light. And this is the current injection difference between right circular and left circular. So again, this is like the graphene case. In metals, I don't think it's possible to get 1 part in a billion. I would love someone to prove me wrong. Metals have too many other competing effects and perturbations from disorder and so on. But I think at the 1% level, not only would this be large, but it would be great to see a natural scale that would extend topology and quantization to nonlinear optical effects. Now, a deeper question maybe is, this was all derived at the single electron level. In the first part of the talk, we know how to generalize topological phases very well to strong interactions and so on. We don't know how to connect this to an anomaly or something else that would be obviously stabled interactions. So here are a couple of better pictures. It winds up being topological in the sense that it only counts something related to the Berry curvature around the Weyl point, so it doesn't matter if you have quadratic perturbations and things like that. It really is a topological quantity. Ultimately, the complicated integral that you have to do for nonlinear optics gets transformed into a very simple topological integral, very much like happens with Thouless's work on quantum Hall. And there are materials that should show this, so we're hoping someone will do the experiment. Now let me go back to the experiment that is out there, and this is an example of how experiment is important and tells us things we didn't expect. Our theory would say this material won't have the interesting topological response, and it doesn't, but it has an enormous ordinary response. In fact, this new Weyl semimetal, this is a paper from Joe Orenstein's group at Berkeley, has the largest second harmonic generation or frequency doubling ever measured, about 10 times larger than gallium arsenide, and that's actually a technologically useful effect in addition to being mysterious. So Weyl semimetals are already good for something, even though they're only about 2 years old. So to wrap up, what I've tried to say in the new part, so the old part is that there are these Berry phase gauge fields. They underlie topological phases, at least the simplest kind, and those are measured and very precisely. But even if I go beyond insulators and I go to metals, where at first glance not much would be topological, some interesting things happen. So first, at linear response, which is where we normally like to work in physics, I think, there's not that much new, I think, in Weyl semimetals. You can go to maybe higher order in momentum, but it's easier to go to higher order in field. Higher order in field, there is a new effect, but we don't quite understand the full ramifications of it. And then finally, in this talk, I've focused mostly on one electron behavior, but things get even more exciting. For example, you get the fractional particles that Shankar talked about when you add stronger interactions. One electron physics, however geometric or topological it may be, is often sort of the framework to find new correlated states. For metals, maybe we don't necessarily get new phases, but we get new kinds of hydrodynamics and new transport laws, like what Leon talked about. So with that, let me say thanks again to ICTS, and I can take a few questions.
Yeah, I didn't follow the technical details of the nonlinear optical effect, but the fact that while semimetals are not immune to disorder because of rare region, this is now, there is no question about it. Even the surface Fermi arcs will disappear. We'll have a paper posted tonight. I mean, would that affect what you're predicting, or are these effects not robust, crude enough that subtle effect of rare region, the Griffiths phase, doesn't matter?
Well, the good thing is we're at finite frequency, so that helps a bit. So DC transport gets much more strongly affected in the surfaces. So
I forgot it's finite frequency.
Exactly. So basically, omega tau greater than 1, but I think even then, I think there's a part of your point that is very well taken, which is the corrections are not exponentially small like they would be in an insulator. I think they're 1 over omega tau squared.
But in a broad way, they will see something because it's finite frequency.